Welcome to Pipeline Conversations, a machine learning podcast by ZenML. This week, I spoke with Mohan Mahadevan, a senior VP at Onfido, a machine learning-powered identity verification platform. He has previously worked at Amazon, heading up a computer vision team working on robotics applications, as well as for many years at KLA, a leading semiconductor hardware company. He holds a doctorate in theoretical physics from Colorado State University. Mohan had mentioned that he thought it might be interesting to discuss Neurosymbolic AI and the implications of a shift towards that as a core paradigm for production AI systems. In particular, in this podcast, we discuss the practical consequences of such a shift, both in terms of team composition as well as infrastructure requirements. I really enjoyed this discussion, and I hope you do too.
So my name is Mohan Mahadevan, and I run the applied science team at Onfido right now. Onfido is a digital identity verification company. So it's a digital onboarding company. It allows consumers to access products and services online by proving who they are. It could be anything from opening a bank account to opening buying cryptocurrency online, to renting a car, to a whole host of services and products that you can access online. And so at Onfido, this is done through validating your document and your face. So a government issued ID, you take a picture or a video of a government issued ID and a picture or a video of your face. And then behind the scenes, we do a few things. One of them is we match the biometrics. That means we match the face in the video or the selfie to that in the document. We extract the data from the document, like your name, date of birth, your address, etc. And then we do fraud detection on the document to ensure that it hasn't been tampered with in any way. And this is a very challenging problem because we have to scale to think of over 10,000 documents across the globe. So there could be Tanzania passport 27.
Document types, you mean?
Or, 10,000 document types. And you have to know the details of every document type in order to know that it hasn't been tampered with. And so it's a very challenging scale problem. And another aspect of this is doing biometric anti-spoofing. So someone isn't pretending to be someone else by either grabbing a picture of Facebook or from the web or putting on a mask, theatrical makeup, a whole 9 yards. You aren't trying to spoof and be someone else. And then in addition, all of this is wrapped up through a risk engine or a decision engine, wherein we add a whole bunch of other signals like your IP address, your where are you accessing from? Is there something suspicious about the behavioral biometrics or whatever, right? So a whole host of things slowly get added on to create a complete digital identity verification product. And so machine learning is, of course, at the heart of it. And I've been doing this for about 3 years now at Onfido and absolutely enjoyed it. A host of challenging problems for us to solve, and also deploy these at scale for our global customers. So that's at Onfido. I've been there for about 3 years. Prior to that, I was running perception and control systems for robotics at Amazon in Seattle, where we were deploying robotic applications in the warehouses to automate things, to automate tasks in the warehouses. They could be stowing, packing, moving, etc. And prior to that, I spent a long time in the semiconductor industry, worked in a company called KLA. And most people haven't heard of this company, but because it's in the semiconductor capital equipment space, which is a B2B space. But that world, I was there for over 18 years, and I saw Moore's law go from 350 nanometers or so when I was started there to about 5 nanometers in research and 7 nanometers in pilot lines when I left 18 years later. And so there we built inspection and metrology equipment for the chip makers. So as you're building the chip, you need to ensure that every step in the chip was built correctly. There weren't any problems that happened. And so we'd have to physically image the wafer and detect problems, anomalies, defects, variations in process, so that our customers could then take preventive actions and corrective actions before they took the chip all the way and then found out something was broken at the very end. So that was a very challenging and exciting time, which any day I could come into work and have 4 to 5 to 10 really hard problems to work on. And it was really exciting and challenging to work there. So, in a nutshell, that's my background. In a previous lifetime, I also have a PhD in theoretical physics. But I think the physics community would probably not call me a physicist anymore. Because
Well,
I've been
presumably you've brought some of the skills from that work into your new life.
Absolutely, absolutely. I recently met up with my advisor, actually, and I was telling him that there were so many things I learned from him during the course of my PhD that I still use every day. And so, very true. Very good point, Alex.
Are there any ways where you could see there would be a lot of ways to bring things back to theoretical physics somehow from your current work that maybe aren't part of the way that theoretical physics gets done?
Yeah, so I think machine learning in general has already moved into physics in a big way, both in experimental and theoretical physics. So DeepMind is using machine learning to detect new materials. They're detecting, being able to run simulations through machine learning that would take a very, very long time to run, classically with the old methods, traditional methods. So there's a host of areas where machine learning is impacting physics in a big way. This includes particle physics, cosmology, a whole set of areas within physics. But I'll tell you an area where it's very practical. So even in the semiconductor area, there are lithography simulations where you send light through the mask, and then it puts a pattern on the wafer. It develops a pattern on the wafer, and in order to do that simulation classically, it would take a long time, but machine learning is bringing amazing speed ups and accuracy to those simulations in order to search the space of parameters. And so machine learning is already deeply in physics in many ways. Yeah, but I'm personally not involved in that right now.
Mm-hmm.
But yeah,
Mm-hmm.
perhaps in the future.
And perhaps as a bridge to, I guess, what we wanted to spend the bulk of our time talking about today, I'm thinking, I forget the exact name of it.
In the case of DeepMind's AlphaFold,
maybe you could take a purely no assumptions taken about how to predict this, and you just work from the data and you classic neural network to try to make those connections. And then maybe there's another approach which really takes a lot of the stuff that we already know about the physical and biological universe. I don't know whether you want to think about this as a rules-based approach, but there's some kind of knowledge graph or something about, we always know that molecules behave in this or that way. And as far as I understand it, there's obviously traditionally been different camps. So you
Yeah.
mentioned that you wanted to talk about neurosymbolic AI. Could you maybe talk a bit about how these things relate to each other?
Yeah, certainly, certainly. So I think so. Maybe I'll just recast your question a little bit in the terminology that I'm familiar with. So I'll call one area sort of end-to-end learning, where you just drop in the data, give it a objective function, and let the neural network learn the function approximation to transform, go from data to insight, result, molecule structure, what have you. And then there's the other approach, which is let's take all the priors and information that we have and build these complex rules, and then within those rules we'll have to do all kinds of searches to see within the parameters to see if there is a new molecule or if there's something else going on, or build a system that can now act intelligently in the world, right? So symbolic, it's called GoFi, good old fashioned AI, or symbolic AI. And I think both of them have their advantages and disadvantages. And so I would say that there are, it, so if you look at the end to end learning, there are lots of advantages, because you don't have to put in a lot of old knowledge in there. It takes time to build that in. It takes a lot of heuristics to build that in, and suddenly you're in a place where it just takes an immensely long amount of time to make something happen, and you may not be able to make it happen because you cannot encode all the world information in rules. right?
Like for
Yeah.
computer vision problems
Yeah,
or
computer
whatever, right?
vision problems or yeah. So the neural networks, what they allow you to do is they allow you to discover these things, discover these correlations, and discover them from data directly without having to hand engineer and symbolify everything within the network. Now, this is amazing because I'll give you I'll give you a practical example. If you want to solve a business problem in an afternoon, somebody can pull data from a data repository, pull a model from an online repository, and train a model. And by late afternoon, we can have results. Okay, that's how quick some of these solutions can be, these end-to-end learning, and especially with the great democratization of machine learning that has happened, with people open sourcing their models and data sets and things like that. But on the other hand, there is a downside. This is not without cost. The downside is that there is no sort of what I'll call systematic generalization. There is if you really want to make this production grade and high performance, you need lots and lots of data before your models can converge to that really good solution. These neural networks can have issues with adversarial perturbations where a small change of a few pixels in the data can cause the answer to be completely wrong. And there are lots of examples you can see, lots of really stunning examples. And there's a paper in 2014 from Google that shows that by changing a small number of pixels in the right way, you can take things like a school bus, which was correctly classified as a school bus, now is called an ostrich. or a building is called an ostrich. So they moved 6 completely different things to be called ostriches now, and with high confidence as well. And so, and then there is another thing, which is what I'll call lack of transfer learning. Okay, so which means if you've learned to do one task, you're good at that task. And you can't take that knowledge very easily to another task. So these end-to-end learning systems have a lot of advantages in that you can go quickly to a solution. You can let the function approximation learn the function rather than have to hand engineer features and things like that. But again, there are some downsides. And on the other side, the symbolic AI gives you all the explainability and the transfer and all of that very well. But there is a downside because you can't encode the world knowledge in rules. And it's impossible. And every time something changes, you can't change the entire system, right? And so there's a downside on that. And so if you look at this, as you mentioned, neurosymbolic AI systems, this field attempts to bring the best of both worlds and thereby take the benefits of the neural network where you don't have to handcraft and hand engineer things and lose the ability to transfer or be data efficient or explain. And on the other hand, it brings the value of neural networks in that it can deal with noise. It can build the functions where it is impossible to symbolify and create this, encode the world's knowledge and rules. And so it's able to bring the best of both worlds in such a way that you can build practical machine learning and based solutions to real world problems.
And I guess there's a spectrum of kind of hard battle tested and kind of purely speculative research ideas. Where is this right now?
Yeah. So if you look at the practitioners, if you look at, let's say, some of the products that actually work in the real world, okay. So Google Search is a product that works in the real world. I suggest that Alexa and Google Voice and Siri and these products work in the real world. And so these are sort of public-facing products. And then there are B2B products, lots of B2B products, all of which actually use neurosymbolic AI without calling it that. Mm-hmm. So a lot of these high-performance products that have to work in the real world are already using neurosymbolic AI. They don't call them that. So I'll give you an example. In the semiconductor world, when we were building these inspection systems to detect defects and do them at sub-resolution, which means a defect is smaller than a pixel, but it leaves a certain amount of signal, and you need to be able to detect that with a low error rate, with a low false positive rate. So we were using neurosymbolic AI systems without ever calling it that. And the way it would work there is you can imagine that the context of where a certain structures were in the semiconductor wafers were important. And so if you can focus on that with the rich priors of knowing where the context is, then you bring that rule. It's almost like a rule of where that prior was, where those structures were. And so you could focus differentially in the entire image. And to some extent, this is also attention, what attention or the transformer networks attempt to do. They like to focus on the areas that are more interesting, except that in the transformers, they want to learn where to focus. And in neurosymbolic AI, you can tell the system where to focus. And so you get this data efficiency because you can bring this prior, and by mapping and aligning the prior into the incoming image, you know where to focus on, instead of having the transformer networks actually tell you where to focus on. So again, this is about practicality. The academia and the folks who build the transformer architectures are trying to solve a much bigger problem, but in real life, you don't want to boil the oceans. If you have to build a problem to solve a business problem in real world, you just have to solve that specific thing. And so you don't have to build general AI to solve that. But if you are very careful about how you build these neurosymbolic AI systems, you can get to a solution much faster that offers these advantages of transferability, explainability, bias mitigation, and data efficiency.
So it seems like from the way you're saying it, and at least that meshes with my experience of having started to read about it, a lot of people have either been applying it or been bringing it in as part of their pipelines or their systems as a kind of a natural extension of what they have because it helps suit their problems. Is that the right way of thinking about it?
That's the real world scrappy way of how things are moving. Yeah.
Okay. And are there specific problems that this approach is kind of born to solve? Is it better in certain areas versus others?
Yeah. So I think that's a great question, and the way we can think about it is even in end-to-end learning systems, we always like to use priors, which means if you have any prior information that you can inject into the network, then the networks learn very data efficiently, but also learn what you want them to learn. As opposed to trying to figure out function approximations blindly, it's a guided function approximation. And what that does...
As features, do you mean?
It could be features, it could be meta variables that you know, it could be an additional pre-processed image. I'll give you an example. Supposing you want the network to learn frequency variations. Okay, that means that when I'll take the example of our document fraud detection. So what happens is a good fraudster might download a template of a document, might make edits that are very, very good with Photoshop or whatever, and then print out the document on a very good printer. Right? And that seems like, wow, that would be very hard for a human to detect. But what happens is the government printer that printed that document leaves a certain set of frequencies that the human eye can't necessarily see. Okay. And this printer now left a different set of frequencies in this document. So what you do is, instead of just injecting the good data and some sampled supervised fraud data and ask the network to learn, what you do is you compute the frequency in certain areas of the incoming data and feed that as an additional channel. So you can even send in a frequency image. So now the network is very efficiently learning to use frequency data to detect fraud. And similarly, you can send in another channel. You can send in pre-processed channels. You can send in features, metadata, those kinds of things.
Okay.
Yeah. So using the priors is just a good thing, even in end-to-end learning systems. And what Neurosymbolic AI does is it tries to bring in the priors very effectively. So you don't force a network to do a lot of learning, which means that you protect yourself from having to give it a lot of data so that it can learn all of these functions that it needs to learn to do the job properly. You make it focus on the most difficult parts of it, the parts that you can't hand engineer, the parts that are tricky. And so if you feed those in, and if you feed in the priors you have and let the neural networks do what they're very good at, which is learning these functions when it is very hard to specify them, when it is very hard to encode the world priors in these symbolic rules, then you get the best of both worlds. Now, I'll give you a practical example. So we, in our identity verification, let's take document fraud detection again. We have customers from all over the world sending us images taken on every kind of mobile device with every kind of sensor in every kind of lighting conditions and focus drifts and focus conditions. And so as our data corpus builds, it is much more effective to ask a neural network to deal with that noise, because you don't have to build symbolic rules to deal with that noise. You let the neural network learn the spread of the noise distributions, and so it can naturally deal with that. So here's an example where something is hard to encode, and as long as you get a good data corpus, let the neural networks do an amazing job. Another example would be, it's a data dependent thing. If you have a lot of data, neural networks are amazing. Okay, and we've seen this time and time and time again. So if you've got lots of data, don't worry about a lot of symbolic stuff, right? Build in priors so that you get generalization and explainability to some extent, but use the neural networks powerfully. So it's almost like there's no one rule, right? You have to take your problem and know whether you want to go to the left bookend with neural networks or to the right bookend with symbolic rules. And where do you sit in that depends on the problem you're solving.
Mm-hmm. Are there any trade-offs we're making when we take this approach? Or, yeah, I'm just wondering what's being left behind by merging these together?
Yeah, so that's a good question. So let's look at this in a few ways, and I'll talk about both the advantages and the trade-offs. I talked of some of the advantages before, but before we go to trade-offs, let me add one more advantage. Okay,
Sure.
So there's a host of AI governance regulations that are coming, and these are going to be really challenging. Okay, so we've been sort of working in the wild west now. Anything flies, build any network with any data, and it flies, and it's all good. Yeah. Right. Now the but with this AI regulations, apart from data use and intent and minimization like we have in GDPR, and apart from things like ethics and security, we have bias to deal with. Okay, we have how shall I say? It's not enough to build a model and deploy it. You have to monitor it and update it constantly. And you have to monitor bias now. So these regulations are now going to say, how are you monitoring bias? How are you monitoring? How are you correcting for bias? How can you prove that you corrected for bias when you detected it? And so the AI governance is asking for the AI-based, ML-based systems to be responsive now, to understand where their weaknesses are and be responsive. And these end-to-end throw a large amount of data into the solution just cannot offer that, right? And so it's almost as if there is going to be some pressure to use these neurosymbolic AI systems to satisfy the needs of AI governance. So with that context, now I'll go to the other side, which is what are the downsides? So the downsides are it takes time to engineer these. As I said, you have to understand where in the bookend you want to be to solve your problem. That means you're depending on the expertise of the team you have, right? How do they make decisions on whether to use neural networks here or symbolic AI? So we've just made the product building more complicated on the science side now, right? Because there are a lot of these. It's not a hyperparameter. It's not a system that you can just feed in like machine learning systems typically are fed in data and an objective function. So it requires that, and if that intelligence and that human intelligence and that human effort that has to go in, so that's expensive. It takes time, it takes resources, and humans can get it wrong. So you'll never know whether you've built that perfect system. In any case, you can't guarantee that, but now there is a stronger dependence on the human factor, so to speak. That's one downside. Actually, before I bring this other downside, let me set a bigger context. So if you look at what is called deep learning system 2 or system 2, from Daniel Kahneman, or how Yoshua Bengio and folks talk about it. And if you talk of neurosymbolic AI systems, while they look like they're two different things, they're really just converging towards one thing. So where we are headed to in the future is these deep learning system 2 attention-based approaches is nothing but learning the symbolism without having these explicit need to encode symbolism. Okay, so in a way, that's the context of where we are headed. Now we are far away from that. To be honest, I'd say we are maybe 3, 4, 5 years before they're practical in real world applications. But and so until then, we have no choice but to encode these rules in. And so the reason I bring this context is there are people who are trained in different schools of thought. Okay, so as you hire these teams, people come with strong biases about what is the right way to solve a problem. And it's very hard to find people who are yet trained in neurosymbolic AI ways. So if you want to build these teams to take care of the human intellect problem, hiring challenges are there in order to hire the right people who can come in and make this happen. So the people who are very strongly attached to this, end-to-end learning, attention-based consciousness, system 2 is going to take us there, and that's what we need to do. Don't do this encoding of priors and information strongly as neurosymbolic AI systems. So that's the second problem, which is actually finding the right talent pool to be able to solve these. But in the first problem, I kind of put two things together there. Okay, I said understanding the bookend and that there are several challenges there. It's not just the time it takes to build a system, but it is also about how you break the system and how you build a roadmap, because you may start out when you have very little data with high symbolism, and as you get more and more data, you may become more neural network based. And so it's not a static thing that I built the system and I deployed it and I'm done. It's actually it's almost like a ramp, that you start with this and then you get there. So understanding that and engineering that is hard.
Mm-hmm. When I think of encoding hard data in symbolic systems and so on, I definitely have my old historian's hat on and so on, and I can see a lot of risks in that. And obviously, knowledge expands and changes, and the risk of bias and issues with that, I imagine, would be quite high.
Yes, indeed. So it's a catch-22. So you can actually take care of bias by designing the right neurosymbolic AI systems. But then when you bring in the human in such a strong way in there, you can introduce biases as well. So that's where the human element and the uncertainty makes things harder. Now, if you look at in academia, there are at least, I'd say, 2 to 3 approaches from different groups, and in fact, more, I'm sure of. So if you look, IBM and MIT have a big program on neurosymbolic AI systems, and the way they approach it is one way. And then there are, from CMU and from University of Washington, there are a couple of other, what we call common sense reasoning that approach it in a slightly different way with tree-based LSTMs, and where they are proving things out. And so as academia starting, and Yoshua Benjo and folks, with the system to deep learning attention. So as all of these approaches are starting to converge in their own ways, right? Hopefully there'll be more frameworks that allow, that take this uncertainty out from, introducing human biases when we build these symbolic systems and take the expertise out. But in the meanwhile, I think it's hard to walk away from that, especially in the context of this AI governance regulations starting to come. The ICO in the UK is working on AI governance regulations for companies. The EU in Brussels is working on a whole framework on AI governance. The US just released SR 711, but then there are other wins that are coming as well. So I think in the short term, it'll be hard to walk away from that if you have to satisfy some of these regulations.
Mm-hmm. I'm curious, in a practical sense, for a data scientist working on a problem, I guess we've sort of started converging on a kind of a pattern for how to work to apply neural networks to a particular problem, and almost the different boxes you slot your pieces into in order to end up with a certain result. I'm curious how thinking neurosymbolically, like applying this, what does this change about your process?
Right. So let's break this down with one or two examples because it'll be easier to follow in that way. So the simplest way of thinking about neurosymbolic AI in my mind is asking what priors you can build into your end-to-end learning systems. If you didn't have the data, how could you still get the network to learn what you wanted to learn, as opposed to learning spurious function approximations, which are correlations that don't exist in real world, but they are fair conclusions that the network learns because of the limitations of data you have, because of the incompleteness of the data set you have, right? And so ask yourselves, what priors can you inject, as opposed to just sending the data raw with labels, okay? And so that would be the simplest thing, and keep asking yourself that constantly as you get more results. Let's say you start with a very simple system. You build an end-to-end system. You have some labels. You define the problem as a classification problem. Let's take the document fraud example. Okay, so we define it initially. I've got a bunch of fraud data of, let's say, UKDLs. I got a bunch of genuine data as UKDLs. I have a convolutional neural network, and I say, let me classify the fraud from the genuine and use this network to do that job. And then I look at the errors it makes, and then I look to see what it didn't learn. And typically what we do is, today we augment that data. Oh, you made errors here. You didn't have enough data of this type or that type. Okay, I'll augment it and then I'll retrain it. And now I don't have errors. But as you start to look at those errors, ask yourself, are the errors coming from some area of the document, for example? Maybe more errors are coming from the picture area. So then you might break this problem in a very simple way. You might say, let's separate the picture area and let's separate the document. Let's have two models. One that focuses on the picture area, that where it can specifically look for issues with the tampering of the picture area. And so you've now built a better system, because now your picture area model is doing a single job, a simple job. You can use a smaller model, lesser data, learns more efficiently, and is sensitive. And you built your first neurosymbolic AI system because you bought in a very valuable prior.
You've semantically separated
Yeah,
out
exactly. So it doesn't have to be something very complicated. You don't have to think of neurosymbolic AI systems as something very, very complicated, but you're building in intelligent priors in the data, so that in the input channels, so that either you have multiple networks, which is now part of the bigger system that generates the answer whether a document was fraud or not. And so you can start very simply from there.
In terms of the kind of the hardware or the infrastructure requirements of this, what my mind immediately goes to thinking of knowledge graphs, database, and so on as the pairing here. Even if we assume that it doesn't necessarily change so much to your process, does it change things to the infrastructure?
Yeah, so there are a few aspects here. If you look at the infrastructure, so let's take training, deployment, and monitoring. So let's break it up into three different parts. So for the training now, the training infrastructure is a little bit of a, today, if you look at the standard machine learning solutions, they're pipelines anyway. There's a pre-processing step, there's a prep step, there's a model, there's another model, there's, blah. So there's already a pipeline. So you can think of this as a little bit more complexity in that pipeline. So in that aspect, not a whole lot changes. However, as these folks, as the data scientists, as the machine learning scientists, build in more priors and interesting symbol knowledge into the neural network, into the pipeline, they need to be able to configure this and change this very quickly. So one of the infrastructure needs was, you think of a pipeline as a static thing. Now you want to think about it as a very dynamic thing. And so what do you do to make that super dynamic? So these folks can change that, if necessary, on a every 2 days, right? They discover something new, they say, oh, don't fight that problem this way. Let's just drop a symbol, train a network, and suddenly this thing is growing and adapting and changing dynamically. So the there has to be what I'll call a level of configurability that doesn't require ML engineers to be involved, so that the ML scientists can not only build these and test these, and so the number of iterations, I think you can expect that to jump up. So you need to build the infrastructure in such a way that the number of iterations jumps up dramatically. The deployment, again, if you think of the cloud deployments, which are the most popular deployments, if you've got a very complex pipeline, suddenly you've got latency issues, you've got how you use your compute. Do you use a GPU-based compute or a CPU-based compute? Because some of these symbolic algorithms are very good on CPUs. Mm-hmm. And you can't port them on GPUs. So how do you balance compute out so that you don't lose latency as you deploy these applications? So the inference pipelines will most likely require flexibility, but also some engineering in terms of being able to use the hardware effectively. So CPU, GPU, and latency are at least the minimal requirements there. And second, imagine if I now have, instead of having one large model, okay, I have 50 small models. Mm-hmm. Suddenly there could even be a memory problem, right? And so inference pipelines will be challenged as more folks start to build these neurosymbolic AI systems and deploy them. The last is in the monitor and the correction, right? So you have to monitor and then you have to correct when drifts occur. And that correct step is actually a tricky one. So monitor is a little bit easier, but now you're not monitoring one high-level performance. You can monitor performance of 10 models below it. So you can go change that single thing. And so this is the advantage and the disadvantage. The advantage is now you know where to go fix things because it's explainable and it's interpretable. But it is hard to on the infrastructure because now you have to monitor 10x, in terms of models that have drifted and things. So more automated and intelligent monitoring would be required for these systems. And the correction is more interesting. So correction is multifold. Correction is you get some failures in some area. Now, if you add more symbols and move to the right where you're going towards more of the symbolic AI, then suddenly you've changed the pipeline. And so in the previous world, what would happen is we'd augment the data and update the model. Things didn't change a whole lot. You just updated that one model in the pipeline and deployed it. Now, all of a sudden, you've changed the pipeline. And if you've changed the pipeline, now you have to again worry about how this fits in your memory and the latency and all of that. So that could be that. If it goes down that direction where people are changing things frequently, improving performance, fixing problems, then you're looking at more complexity in the monitor, correction, retrain, deploy phase. It makes it more complex.
It definitely feels like we have this whole field now. It has a name, MLOps now, where people are starting to worry about this problem. It definitely feels like it's a little bit behind what people are trying to do practically. Like they're solving their problems and then they find they have to solve this other infrastructure problem along the way. With this discussion about neurosymbolic AI in mind, is it really just the dynamism of this that is kind of the core thing that needs to be addressed?
So yeah, okay, yeah. So I agree. It's a dynamism, but there are a few decisions there. How dynamic should it be? How dynamic does it? How much does the dynamism change? The needs, and unfortunately or fortunately, this thing has to run in inference. In a fixed infrastructure, right? And so that dynamism has impacts both in the training phase and in the deployment phase. And there is another aspect, which is, the holy grail, so to speak, is the ML scientists, when they train the model, they can deploy it without engineering overhead. Okay, that's the holy grail, right? Hardly ever happens. But now with these systems, I think we don't have a choice. We have to make that work.
Mm-hmm.
It has to be able to go without engineering overhead in a way. And so my vision is that we build a certain degree of configurability. And so the data scientists, they before they deploy, of course, they have to do the functional testing, regression testing, uh, take care of the performance tests, and make sure that you don't have the catastrophic forgetting problem. So that has to be automated. So let's say the data scientist looks at some problem in production, comes up with a simple fix, which is obvious. And now all of a sudden you've got to automate that deployment piece in such a way that
Mm-hmm.
it doesn't have this engineering overhead. Otherwise, this solution that could bring business value could just be stopped or delayed, right?
Mm-hmm.
This path would become so suboptimal that if it takes 2 months for every small cycle to go to deployment,
Mm-hmm.
then I think this will die.
Right.
The baby gets thrown out of the bathwater, basically.
Mm-hmm. Are there any human requirements around this? I'm thinking currently it seems there's a kind of a trend to try to take domain experts and make them think about how to reason about and how to train models. And I guess maybe that's sort of a neurosymbolic system where you're bringing in someone with that domain expertise who's then able to work in a certain way. Does this require different configurations of how ML teams work, different specialisms, anything like that?
Yeah, that's a great question, Alex. Really great question. So, because I worry about this a lot, and it's behind the scenes, right? People don't think about this. So, this is my current read on this. It's not that neurosymbolic AI systems are going to cause that. It is
Mm-hmm.
that the AI governance regulations are going to cause that.
Mm-hmm.
So, right now, if you look, our scientists are not necessarily trained on ethics of AI,
Yep.
on bias, right? And so, as these governance regulations come to play, I think we'll have to bring new groups of people in to the ML development flow that would ensure that we are able to adhere to these regulations, both in the letter of the law and the spirit of it. The
Mm-hmm.
spirit of it is almost more important, because if you ask each ML scientist, no one wants to be racist, okay?
Mm-hmm.
But how many models out there are racist today,
Sure.
right? And built by these very well-intentioned
Mm-hmm.
ML scientists, right? And so my suspicion is we'll have to bring in that expertise either through training programs and experts that work with the ML scientists and the engineers, and they might then influence how these neurosymbolic AI systems are built and monitored and corrected.
Mm-hmm.
So, yes, there is a human aspect. My read is that it will come from outside. I mean, the ML scientists are all anyway constantly evolving, right? Or whether it be LST RNNs to LSTMs to transformers or whatever, it's constantly evolving. So that part, I think, is we are used to it. We'll constantly evolve, whether it's neurosymbolic AI systems or neural networks. But there's this other element of people that have to be involved in these companies as well.
Mm-hmm. And are there any other things which I guess need to happen for us to head further into this future? At least it seems like you're saying that it's inevitable we're heading into this in any case. But I'm just thinking of a lot of people, fresh minds who are coming into this field right now. There's definitely an overemphasis on the kind of the end-to-end models and learning systems that you were talking about over the other, and there's not really much reward for exploring the other side. So
Yeah.
is that a risk?
Yeah, it is a risk, but it is no more of a risk than what existed before, honestly. So
Okay.
if you look at academia, and I'll tell you what I mean by this. If you look at academia, um, the PhD and the postdocs that we hire, right? They they are they are working in terms of pushing the limits of ML, right? Where is the frontier of ML? How do we push it further? And so their focus is entirely different, and rightly so. They should be focused on that. And when they come into industry, to build real world products, there's a huge training and learning, on the job training and learning that has to happen anyway, right? These folks, even who know how to build end to end learning systems, they don't have to worry with the failure of the IID assumption, okay, which is outer distribution detection. They don't worry about that, because in the papers, you just need to take that data and train till you can push the benchmark somewhat higher, new neural architecture, what have you, so that problem has always existed. This is not making it any worse necessarily, because the dynamics and the actual pragmatism of building real world solutions based on ML is very different from what students learn in academia.
Mm-hmm. And it definitely seems to me like there's also a tooling gap somehow in, particularly, I mean, we were talking about democratization earlier. There's definitely some kind of gulf in between, which if you could blend it, maybe with tools, maybe with education, maybe with something, that you could get further along towards that end goal.
Yeah. So if you look at the current products that have neurosymbolic AI systems, they've all built internal kludgy tooling to make it work for them, right?
Yeah.
So here, I think your question is referring to generalized frameworks. Now, yeah, there is a need for it, but right now there isn't a single solution of how to do this, right? Even if you look at the way IBM approaches it, or if you look at the way the CMU group approaches it, or if you look at the way the University of Washington group approaches it, just a few examples. There are many groups working on this. I don't want to shortchange anyone here. They all have different approaches, right? And so this is still very young and fresh in academia, and so I think we are not yet at a place where I would say that there's a framework, even though there will be a claim of frameworks, right, from each of these groups that definitely feel passionate about the way they're going about it. But I don't think we are in a place where a generalized framework that works like TensorFlow or PyTorch or whatever is going to be of the. So this is still going to be kludgy for a while. And over time, maybe it will be mature enough for a generalized framework to emerge.
But do you see that as a necessity eventually?
I think I won't call it a necessity, because you can work through a mishmash of internal tools and mechanisms, but I see it as an eventuality.
Okay.
As these AI governance regulations force us to behave in what I'd call principled ways, the frameworks will have to provide ways of developing these products in a principled way.
Just to take it back to kind of where we began, is hardware any of a bottleneck in all of this? We have this kind of Cambrian explosion of tooling right now. Are we seeing similar kinds of new pathways and so on to help us deal with this?
Yeah. So here I'm going to reflect my age a little bit. So you know this hardware software generic versus specific. It also goes in cycles.
Okay.
So I remember in 1995, we had to process 400 megapixels, million pixels a second in real time, and so we had to build custom hardware. Then suddenly the CPU scaling happened dramatically. We'd play this game every 6 months. I have 1.2 gigahertz. Now we got 1.8 gigahertz, 2.2, so on. And so when that started to happen, suddenly this custom hardware couldn't catch up. Okay. Then the GPUs, the story of the GPUs. And then now if you look, every company has built their own hardware almost, right? Whether it be Google or Amazon or, and so a lot of companies are building these custom hardware kits for machine learning, right? And also on the edge. So it's specifically for these systems, today we ignore the hardware question when it comes to developing. We just assume the cloud's going to have the latest and let the latest just evolve.
It's going to continue.
Yeah. Then my suspicion, this is again my prediction, so to speak. I could be wrong here. Is we've ignored latency so far in a big way for a lot of commercial applications, but latency will become more and more valuable because if something is faster, then people will like it more in terms of consumer experience. Now the Google searches, of course, and Netflix, they worry about latency all the time. That's why they build their own hardware to some extent, right? But even our your thousands of startups across the world, at some point they're going to start worrying about what can latency offer in the cloud. So I see this go two ways. One way is the cloud providers now start to have optimization teams that offer these different configurations for these systems that again make it transparent to the end user, to the ML scientists, not the end user, to the ML scientists. I think that's a better solution. But before we get there, I suspect there will be another step where people will do some level of optimization. So there are again companies that do startups that do optimization. They do all the way from neural architecture search to pipeline optimizations. So there will be some of this taking off, and then hopefully the cloud providers will start to provide these really configurable cloud offerings that can offer low latency for customers like on Fido, right? We build all of these models and all of these things, and we want a super low latency, and it shouldn't be on us. Like, why can't the cloud provider provide us, CPU, right. GPU, Yeah. So, yeah, but because today you can do super low latency, but it gets very expensive, even on the cloud. So there's some room for optimization there.
And I guess still in this hardware space, since you did have this experience working in this kind of robotics area, like I'm interested how that changes things, particularly from the perspective of a data scientist, like working with kind of real world hardware. Does that slow things down? Does that add certain constraints to how you work?
So I'll simplify your question to provide an answer. So let's call it the edge compute question. Okay. So how do you take these kinds of more complexity in a way to down to the edge and be able to deploy it on the edge? Yeah. It's a good question, and honestly, I don't have an answer. I haven't thought of this, so it's a very good question. I'll think about this. It's a good question. So today, if you look traditionally on the edge, there are two approaches. One approach is make the model smaller till it works, okay, till you can fit it in the memory and the latency in the edge. Or there are some clever tricks in the neural architecture search that people use to optimize. I think there's a company from Israel called Desi.ai. I recently saw some of their work on that. So that is the approach that is today, that's active today. In the future, and if you look at how the edge compute themselves are going, if you look at Apple's chips or if you look at Qualcomm, they're all bringing in GPU and CPU combinations. So you're getting both of these compute units. So I think there is room for that to mature, but that maturity, the optimization maturity, almost happens after algorithmic maturity. Mm-hmm. So if your algorithms are mature and able to deliver the performance, then you go into optimization, computational optimization maturity. Otherwise, if you keep tweaking this and you spend all this time figuring out a neural architecture search, then you're going to have to redo that process, and that's a very expensive process to deploy onto hardware. So ideally, I would like the hardware to just be transparent to the ML scientists, so then they can just focus on making the algorithms and the models better, and the hardware just takes care of it. And maybe there's investments in optimization groups that take that solution and make it faster. So I guess I'm just riffing here.
Mm-hmm. Yeah, and I wonder if there are really different ways of thinking about it that we haven't even started to bring in. You have federated learning, just to take one kind of example of doing things quite differently somehow, which may play into this kind of edge device question.
Yeah. It's a very, very important one. I mean, differential privacy, which could drive federated learning, and these AI governance regulations. Yeah, it's interesting. It's a very interesting world, how those things evolve. And there, I believe neurosymbolic AI systems will have a role to play. Okay. Because today, federated learning is a tricky beast because you've got these big models that you're trying to get right. Okay. But imagine if this was a neurosymbolic AI system that encoded the local information locally and then didn't have to take a lot of the neural information out there, it could be it could provide an advantage to some of these edge compute things. So there is an interplay there, and it'll be interesting to see how that evolves over time.
Yep.
Yeah.
Great.
Yeah. Yeah.
So we have two final questions we usually ask all of our guests, just short answers, I guess, but yeah, take it however you would like to. The first of these, we like to ask, what would be a quick win that someone could add to make their productionizing of their models more robust?
So based on my experience, it is solving the know when you don't know problem. So machine learning models, they are trained on a corpus of data. And by definition, they're almost forced to remain within that data. Okay, that means that whenever data comes that doesn't belong in that corpus, their performance could be anything. It could be very unreliable and therefore very unrobust. And so you must solve the know when you don't know problem. So a machine learning model must be able to raise its hand and say, I don't know, or I don't trust me on this one at all. And so what so that is the most important problem in my mind to make models robust. And one approach is you can build a confidence model that stands out. So it's like a model watchdog system that stands out of the system and is able to say, trust the model here, don't trust the model here, trust the model here.
Right.
So today this happens sort of incestually, which means that the model itself says whether you should trust it or not, and that's a problem.
Yep.
So I think that is
Interesting. And I mean, maybe that's the answer to the next question as well somehow, but what would be one part of putting a model in production that you think should be given more attention by tool makers in this space?
Yes. I'm very passionate about this. It has to be that the scientists have a set of automated tools that allow them to deploy straight to production. And these automated tools, they must cover functionality testing, they must cover regression testing, performance testing, and catastrophic forgetting testing. Which means as you update a model, it can forget its old performance on old data, and so you must ensure. So if you can automate those four pieces in a way that allow the scientists to train models, it's almost like it's a gate. After they retrain a model and say, yes, this looks really good, let's go to production, you've got to remove the engineering bandwidth. Engineers should not be forced to do this kind of tedious task of taking that model and productionizing it. It should just go right through. Engineers should be building the automation to enable these scientists to be able to take those solutions straight to production.
Just like, I guess, we're not really programming in assembly or
yeah
anymore.
exactly. So to me, that is the holy grail of our future, and we need to be able to enable that.
Okay. Great. Well, thank you very much, Mohan, for taking the time.
Yeah, thank you for having me, Alex, and it was a pleasure.
Thank you for listening to this latest episode of Pipeline Conversations. If you enjoyed what you heard, please consider giving us a review wherever you get your podcasts. It helps us get seen by more people, and of course, it's always nice to receive feedback. If you have suggestions for future guests, please send them over to podcast@zenml.io. Thanks. Until next time.